it works. And so, as a consequence, the thing that we're going to cover is going to be game theory for non-cooperative games, because definitely the games that you're developing are non-cooperative games. Most of the times are competitive, and so that's why we're going to focus on this. The other good part is that cooperative games, so if you're using like Nash equations, are actually more complicated to set up. So that is also the easier part. And as my custom, we're going to see a bit of theory behind it before knowing how to apply that to min-max trees. And we're going to see like alpha-beta pruning as a potential algorithm on which you need to be careful about. So the idea is that in here, we're going to assume that the agent is completely, rational, and therefore I'm completely seeing all the possible set of moves that they could also have in front of me. So what is actually the assumption of the algorithm that has an infinite amount of memory, as much as possible, and it could forecast in the future all the possible moves. Under that assumption, then is always making the right choice. So this algorithm is designed in a way that if you're providing the correct setup, is going always to provide the optimal solution, which is not always what you want to expect or what you're expecting, but we're going to see another way when I could filter out how much I could see in the past using another approach like reinforcement learning, with which I could also calibrate how much in the future I could forecast using also the value from a reward function. And so in here, just to provide similarities, we're going to see how that applies with a very simple game like paper, scissors, and rock, paper, and scissors, with a simple matrix, and then we're going to motivate why then we need trees for more complicated games. But exploiting all the possible outcomes is not feasible, so you have another algorithm supporting you, which is actually alpha-beta pruning. So you are still ensuring to visit all the possible pathways, but you're discarding the pathways that might be suboptimal. So that is actually the only optimization that you're doing. And still you are, then we're also going to add randomicity, but so how to exploit the same approach that you're doing, but adding like random choices. So then we're going to see how to extend a discrete environment into a random one. So usually a lot of people are starting from the randomic behavior or probabilistical behavior, and then we're doing everything with that. But first you need to think about how to work without probabilities and then adding probabilities when you need it. If you're doing otherwise, then you think that all you have is a hammer, so everything becomes a needle, but that is actually not the spirit. So depending on the use case that you have, you need to apply the best algorithm. And similarly in here, you're not forced to use one specific algorithm that you're going to see there, but my suggestion will be to use like the most suitable for your needs. So that's why I'm saying from the very beginning, that is actually coming from game theory, from Nash theory of economics. And then they're also seeing with the time that that is not also applied to economics, but also to like growth of populations of animals and things of the sort. And always when you have competition for resources, when you have opposing driving forces to do something, then that is actually when you're having the application as use case scenario. So even though the framework is very general, and it was originally focused for economics, then that could also be applied in a broad spectrum of areas. And so they're trying to achieve the same goal. That is actually the spirit. So, and this goal is summarized by a score function. So overall, one agent might try to maximize a goal, and the other one, which is actually of the opponent, will try to minimize the same score. And so the idea is, if under the assumption that I'm rational, then I will try to anticipate the moves, knowing if the agent is doing this kind of move, then it's going to update the global score in a given way. So, and then the idea is that you could also apply that to video games and competitive games. But before even we start thinking about that, so let's suppose, so in here you have just one global score. On the other hand, let's suppose that you have two enemies beating each other in a fighting game, and you have like a health bar, and under the assumption that you're normalizing both health bars between 0 and 1, okay, just to simplify. So if someone is very strong, then I will decrease actually very less the health bar. If something is very weak, then given the same force, I'm decreasing more of the same health bar. So how would you mimic this behavior within one single score? Under the assumption that one enemy wants to minimize the score, so if the health bar is actually either 1 or, so the maximum value is 1, then one wants to minimize the value in some direction, and the other one wants to maximize the value. So what might be one possible alternative? So that is actually something very customary in mathematics. So you have a problem that you are trying to solve, and you're trying to apply another technology. So you're not reinventing the wheel, you're trying to apply something which is existent, so you're just doing like a mapping function between one problem and the other. If you were taught like reduction of NP problems, that should be like coming in a jiffy, because if you want to reduce like a Turing machine, or program running in a Turing machine into 3-sat solvability or anything of the like, then you have like a complete closure. So you might be accustomed, if you were taught that, to reduce one problem to the other. But anyway, what is the mapping from having two health bars to one single score? And with two agents, one trying to maximize the score and the other one minimizing that. Yeah.
The amount of health points you have left maybe is related to the score of the current game.
Yeah, and so what should be the minimum and maximum value then?
So the minimum value would be getting the health to 0. The maximum value would be trying to inflict the most amount of damage on that health.
Exactly. So in the implementation, I'm going to pursue a similar thing, just out of clarity in the implementation that you have of this. So you have like how to exploit min-max trees. For achieving this, the only difference is that I'm having -1 and +1, but the idea is the same that your colleague was mentioning. So one will try to minimize the value, and then it will decrease the value, overall global value, and the other one will try to maximize the overall value. So you will have a tie at 0. In your scenario, you would have a tie at 0.5, because actually then you'll have like the opposing strategies. One is trying to decrease, and the other one is trying to increase. Then the summation of the two values actually becomes 0. In my scenario, in your scenario, then you need to renormalize and to have 0.5. But beside of that, all the things are similar to each other. So that intuition is going to help you also to understand then in a more simplistic game like rock and papers and scissors, using like a payoff matrix, how that might be. So in here, I have only one turn, and after one turn, I know immediately which is the player winning or losing, you see? So if I'm having rock and rock, I always have ties, for which I have a value of 0, not 0.5, but that is just implementation detail of the value. If that would have been 0.5 and 0 and 1 instead of -1, 0 and 1, would have been the same, but that is actually more straightforward to see. So it's just a matter of conversion of the values. Still, it will be minimizing the value in here, minimizing with -1. In the other scenarios, I would be minimizing with 0, but just a matter of conversion of the values, really. And still, if I have a rock and the scissors, then the rock will win, so the maximizing agent will win. Otherwise, if I have a paper and scissors, then I know that, how to say, the paper and scissors, then I know that the minimizing agent will win, and in fact, the value is actually -1. And then the matrix is somehow inverse symmetrical. So it is symmetrical because I have -1, but in here you have 1, because you have that It's not perfectly a similarity matrix, but it's just like a matrix that needs to reflect that the other person will win symmetrically. So I need also to flip the 0 and 1 values. So in here is very straightforward. I'm assuming that you have like one round of actions. Some agent is doing something like simultaneously. I have rows and columns intersecting, and then I have like the value of the turnout. So in here, then, we might discuss which should be like the best opportunity to do so. But then you could also overcomplicate the stuff in a game, which is still minimalistic, but you need also to think that when IBM created like Deep Blue to beat Kasparov, they were not using deep learning. They were not using AI in that sense, in neural network, all these kind of things, to say the least. They were using like an approach which was easily debuggable, easily understandable. Still, it might be slow because you're not learning a strategy. You are computing that in real time, but you were able to beat Kasparov nevertheless. So the only thing is that in that scenario, you have a lot of rules that were already coded, like, as we will see later on, like how to open the chess, how I'm accustomed to close the game, which are the best moves that are actually guiding force. So I could apply rules sometimes. And other times, I might just hugely and massively paralyze the computation. So I have like different ways. Similarly, if I have tic-tac-toe, then a single matrix will not do. So I need to say that each state, when I'm transitioning from the initial state, and then I have the next move, I might assume that, for example, is the maximizing agent providing the moves. Therefore, each of the possible configurations in that cell is actually providing me a possible outcome of the moves, and then to which the minimizing agent will provide the over next step of the move itself. And then so on and so forth, up until I have a terminal leaf where I have whether the minimizing agent won, or if we have a tie, or if the maximizing agent won. So the O, as in this scenario, is the minimizing agent. Therefore, the value of the terminal cell is -1. If I have a tie, I have 0. Similarly, if the other maximizing agent, which is actually the cross, won, because actually I have a diagonal of crosses in there in the third row, in the third cell of the last row, then I will have a +1. So then you have a fitness function just for the terminal cell. So the idea is that the thing that we were postulating before for a fighting game, where I'm constantly decreasing the score, is just an intuition how to map a problem to the other. Because the thing that is actually happening at the very end is that I have a total score, and that is actually the outcome. So I'm not interested locally on each action, but I'm interested on the composition of the actions leading me to the success. So I'm not necessarily forecasting, that, and here I'm maximizing like my score, and then I might go with that, because globally it might be not the best decision. And so the only thing that I'm interested in is the final score. Then do not be confused. Then you will have like the min-max algorithm or alpha beta that will compute intermediate value, but that is just a mnemonic way, so to say, for the algorithm to remember which was the best action to perform. So I'm just annotating the values to remember later on what should be like the path leading to the best possible route to follow. And then just to make the things more interesting and to add a bit of probability theory, so also to discuss together. So before I progress and add probability to make understand how gain works in game, do you have any other questions related to representation of games using trees or using like the payoff matrix or any of the examples that I provided before I continue? Yeah.
I feel a little confused on what you mean by sort of minimizing and maximizing payoff.
Yeah. So the idea is that if you have like a multi-turn game, then you have in this setup, in min-max trees, you have only one final score, which is actually the total achievement, so to say. So you are not waiting necessarily the actions so to lead into a terminal node. But you might also discretize everything. So I know that in this configuration I won, in the other configuration I lose, so on and so forth. And that is merely a strategy to determine which of the two agents is winning. Is it winning the minimizing agent or is it winning the maximizing agent? Therefore, I know that all the times that the value is the minimum as possible, that will be the best configuration for the minimizing agent. If I have like the maximum score possible, that will be the best turnout for the maximizing agent. So if I have tic-tac-toe, I don't have a scenario where numbers matter, like even in chess. So I don't have like the best choice. I might have, for example, a preferred move, but still at the end, I will win the game or I will lose the game. So the turnout is just, sorry, not turnout. The outcome of the game is just 0-1. I win or I lose. And that is actually reflected by tie, 0, I win, 1 if I'm maximizing agent. I lose, -1. But if you have like a fighting game where, for example, it might matter, for example, even in Final Fantasy or anything of the like, that if I'm fighting now and I'm applying the strategy that I preserves my health bar better, then in the next game my health bar will be still in the same state. So I want to maximize as much as possible my health bar while progressing in the next turn. So in that scenario also how much I could maximize matters, and then the greater the value the better for me. And then I'm adding like a gradient between minimum values and maximum values. Still, among all these possible values, the minimizing agent will always prefer a pathway leading to a terminal node with a very minimum score, whenever that is possible, and a maximizing agent will always prefer to reach a maximum score. The idea is, maybe that configuration is not always possible, because then you have like two contrasting synergies. Another agent opposing with all their forces the other agent to reach that configuration. So you might know that if you're behaving rationally, that configuration might not held, albeit is the thing that I'm aiming towards. So I might want to fall off in another strategy. In this scenario, everything is discrete. I have +1 and -1. But in a realistic scenario, I might have like a degree of values among which I want to prefer, and then maybe I want to prefer a value which is not necessarily 1. If I had to choose, then I would prefer this configuration, if anything. So that is actually what those values stands for. So all the agents will try to reach either the minimum value as possible or the maximum value as possible, because that is where they're winning. And having like a degree of values is just a way to say this is actually the preferred setup. Does that make sense, or do you have other questions?
So basically each move, so if you're the minimum agent, you're sort of minusing score each time and trying to get a minimum score.
Exactly.
Yeah, okay. So if it's a tie, it's always going to be sort of that middle 0 point.
Correct.
Okay.
So all the time, so I know that, how do you say, I might have a game where it might be never possible to win or lose. In that scenario, the best I can do is always have a tie. But then you will see like, so that's why also this kind of algorithms tell you whether, so given that they're not training based, they also give you an insight on how your game will unravel. So if with my game, with that setup, like for example, I know that if I'm doing this action, I'm decreasing the health bar in a given way, and in the other one, I'm decreasing the health bar in a given way, then I'm always having a tie, then maybe the game is not weighted well enough to balance that, so to ensure that one side is winning. Okay? Any other questions? Because now I'm going to show you how to add probability if you're not having a score, just to know how to weight the things. And that is actually when the score becomes relevant, for example. So let's suppose that in here I have like 2 players. One is the god and the other one is the thief. And I have 2 locations having 1 safe each. One safe will contain 10 grand, and the other second safe will contain like 100 grand. And so in there, then the guard is hired, but is not ubiquitous. So they could only choose what to guard and what to protect. And the thief must decide one of the two places. And the thing is, as in rock, papers, and scissors, they need to decide simultaneously. So I cannot foretell which is going to be the action. I could only provide a guess, given like common sense analysis. And so without knowing what the other party will do. So with respect to the game theory, then, for example, we might freely assume, as we say in mathematics, that the thief is a maximum and the robber is minimum. But if you're switching the two parts, then you're going to have the same way. You just need to change the order of the signs of the computation. So you see here, then that is actually the actual configuration. If S1 and S2 means the location. So, and then the thief is a maximizing agent. So the thing that the guard will try to do is to always reach the 0, while the guard will always while the thief will try to get to the 100k, you see. So under the assumption that the thief and the guard are going to be in the same place, that is actually the least case scenario for the thief. So in that scenario, I'm always losing. On the other hand, the guard will catch the thief, and depending on the amount of money that is going to be saved, then I'm gaining the amount of money that was not robbed, basically. And similarly, you could also provide that as a decision tree under the assumption that that are not steps, but are executed simultaneously. Okay. So what is actually then the benefit of using a tree? So the idea is that if you have simultaneous games or simultaneous configurations, if you're using a payoff matrix, so the one on the left, then it's actually describing, as you see, the same configuration that you have on the right. But the problem is, what if I have multiple turns? Then you'd have to have tensors, or I would have to nest tables inside another. It will become actually a complicated mess. And still, if you have a nested table, you could represent a nested table as a tree. So at the very end, out of simplicity, we are always going to assume to use a game tree for our scenarios, even though if you are having a game where everything is decided up front without knowing the move of the opponent, the best configuration is actually using a payoff matrix on the left. But just for simplification purposes, and also to model all the possible turnout of the game, then we're going to use the configuration on the right. But modulo, how to say, potential scene and detaching turns with one single move, then they are almost the same. So in here you might also see something which might be very predictable. And so that's why you might want to, at the very end, to add probabilities. So if I know that, for example, the guard is always going to maximize the gain, its gain, by, for example, saving location 1, then I need to hope that the thief will always go to S2. Otherwise, if the thief is a very rational agent, it will know that the guard will be at location 100, and then it will actually try to I will try to rob at location K. So we'll have like the configuration S1 for the thief and S2 for the guard. So even though the guard doesn't want to lose a lot of money, then it will save like the 100K location, but the thief will always go, if it is actually a rational agent, towards the 10K. So that is actually reflecting the thing that I was mentioning at the very beginning of the class, that adding probabilistical or randomness will help adding variety to the game and making the game less predictable. If I always know that that is actually a deterministic choice, then I'm becoming predictable. On the other hand, if I'm adding variety, then I'm trying not to do so. But the idea is still, by using the power of math, so to speak, I could also know how to maximize my unpredictability. So in here, given that I have a very simplistic game, and that is actually the first bullet point is actually covering what I said in words. So that is actually the idea. Then I need to say I want to protect the safe probability P, and the other safe with probability 1 minus p. So if you're not accustomed, because I know that you didn't do a module on probability and probability, but anyway, so given that I have two choices and they're mutually exclusive, then it will say one is probability p and the other one is probability 1 minus p. So they are mutually exclusive because that value is then always between 0 and 1, and so is already there. So the idea is then how to set up the configuration that I have for the gain to determine the probability of making my decision so to win most of the time as much as possible. So, and then as we will see later on when we will try to model graphs, but those might be quite more convoluted than using like the min-max tree, then also players' expertise could also be modeled by probability. And we will see that, for example, with a minimal example with a game of Pong, where you only have one action, am I catching the ball or I'm not catching the ball? And so we're going to transfer the same knowledge that we're applying in here, P or 1 minus P in the same setup, eventually. And we're going to see also how to model and to show by plotting, which is actually the outcome depending on the strength of the player, modeling that with probabilities, but we'll see that later on. Then we need to infer the strategy that makes the god indifferent to what the thief does at an average level of the game. So we cannot model all the possibilities, so we want to ascertain, okay, in average, then what I'm expecting to have, and that will provide like the best trade-off between the two outcomes. And so this is actually, sorry, that is actually on page slides 12. So I need to reshuffle the slides. So the idea is, how do you set that up? You're setting that as follows. So you know that you want to save. So the thief will get 100 with probability P if I'm actually saving the other location. And then I know that it will have like with probability 10k if the opponent will save the opposite location, so with probability 1 minus P. So I will have that the average gain will be modeled by the probability of the other opponent of saving one of the other two locations. So if it tries to rob S1, as a consequence, I will have like a gain of 10,000 times 1 minus P. Otherwise, I will have 100,000 times P. And so the idea in here just is a way to model the problem. Is not the only possible way to do that, but is a possibility. So I might be indifferent to any one of the turnouts, so it's just the baseline, if the average amount stolen in either scenario is the same. So I'm just providing like an equality value. So I'm just putting that with the equal. So then if I'm doing like basic math, then I could have that the solution is on average, I know that they are almost the same with probability 1 over 11. And as a consequence, by just resolving the equation, the probability of saving the other one should be like 10 over 11. So you'd see at the very end, I'm trying to save the other location, which is actually the more prestigious one, with 10 over 11, and even though it's counterintuitive, that is actually the idea. 10 over 11 for 10 to the power of 4, that implies that that is actually the thing that the thief is gaining, but because that is gaining 10k because I'm saving the 100k, and then in here with probability P because I'm saving the other location, and so the thief will gain with this value. So I know that on average the thief was going to gain this value. So you know at the very end, so then the game is actually not, the code is not doing this kind of machinery. But that is just to make your head twist around the problem itself. So ideally, if you have a probability value, then you could say, okay, on average, I know that I want to prefer one location over the other. You could also use like a rule of thumb number. That is just to have like an exact result on average. But I'm not expecting you to use like math at this level for the coursework, okay? You could also say that one situation is more advantageous than the other. One of the bullet points of the coursework is using like probabilistic or stochastic behavior. Then I could also like use a random number generator, and then I want to generate the number over a uniform distribution, for example, and then I'm checking against the threshold value. If it is below the threshold, then I'm doing one action, otherwise I'm doing the other, and depending on that, then I'm deciding to save, for example, 2 different locations. So that is actually the idea. So then you could also randomize the behavior that you have in a deterministic way. But you see, randomization or probability is something that you're adding on top in order to solve a problem. It's not something that you're adding because you want to add that. And then, because still the decision that you're going to do at the very end is always deterministic. And we're going to see that even with reinforcement learning. Even with reinforcement learning, you have probabilities, you have gains, but then you have like 2 ways. You have like, a final policy, which could be either deterministic, which is always the thing maximizing my score, or it could also have like a gradient between all possible actions. So still in the real world, I need to decide which action to do. So the action should be deterministic, but the decision up front is probabilistic. So that is actually what the problem mostly have a misconception about. So the probabilistic is how I make the choice if either is the same. But usually I know the rationale behind it. And in some cases, either the choice is the same, and so you need to pick something at random, really, because I cannot foretell the behavior of another agent like. So I need to do a random choice. And that is when you're adding probability. Then I know that I'm shoveling back and forth. And then we're going to see like mathematical pseudocode. So hopefully you'll be able to see pseudocode in algorithms, data structures, but I'm not, I don't know whether you're also accustomed with recurrent equations, for example, as you might have seen in time complexity analysis or anything of the like. So, and that is just, and then I'm going to explain that to you for sure, but that is actually how the algorithm behaves in order to decide which is actually the strategy to adopt. Anyone that wants to get a try interpreting this kind of mathematical like equation, which is just like a recursive function, really. So min-max, so you need to think about GC as the current state. I'm providing some design equation for sure. GC is going to be like the state of the game, like the global state. And at the very end, when I'm reaching like a leaf, I know that I have a global utility value. So I have dot global utility, which is actually the value -1, 0, +1, that you've seen before. And then, depending on the agent, whether it's minimizing or is maximizing, is actually doing some actions. And then I know how to proceed because given the current state, I know which are the moves that I could provide, which are not necessarily always the same. It depends on the context and it depends on the game. So given the current configuration, I know which is going to be the next move, which is returning me the next state and the next configuration. So in the game of tic-tac-toe, you're just having like, I want to put a cross, so my next configuration is when the cross is in that place, in that cell, and so on and so forth. Oh, one other thing that I nearly forgot to say is that there is actually a way to make these very humongous decision trees, so to speak, more compact, which is if you're thinking mathematically and you're trying to compress a lot of the configurations as symmetric, are similar or yielding to the same result, and then you're able to compress that. But we're not doing that because it's just bachelor degree. We're not doing research in here. So just having like an intuition how to do is going to be okay. Then if you do need to do that in real world, then it's a different kind of story. So any chance someone wants to interpret what that mathematical 3 lines entail with a recursive function, Everything is written on the slides, by the way. So if you have the slides, then you will need to write everything down. So that's fine. So my suggestion would be, if you're it's completely blank for you, before the how to say the dissertation will start, especially in games, I would suggest you to have a look of pseudocodes, what there are, and how to potentially implement those, because that is actually the real life of a developer. So it's not all the time that you're finding like a ready-made solution which is already in C# or in C++ or any kind of language. Usually have like an algorithm book like Corman, and then the algorithm is in a pseudocode. And then you need to code the pseudocode in your programming language. So you need to understand what the pseudocode means, so you could also do. So you could also write everything like with recursion calls, but in here I'm just returning values instead of saying return, is doing some kind of iterations and keeping values. Before I, yes?
It's a recursive function. Every time it runs, it'll pick the next move based on whether they're the min or.
And how does that behave? So let's explain that to me as it was like code. So I have in the current state, and then what is actually the thing that you have on the right, and how does that apply, and how does make that the decision on the left. So because you're basically repeating at this stage the thing that is already said, but what is actually the addition? What did not I say?
I was just going to say, if it was a negative value, it would run the recursive function again, but as with the new game state that has been obtained from using that function. So, for example, it starts the recursive function with previous game state. It grabs the current payoff value and then determines whether or not to be to run the recursive function again as a minimum agent or a maximum agent.
No, so actually it's not going to, so that is actually more simplified. You are trying to say how that might work into code if you were implementing that and you're trying to add a heuristic. So to preliminary stop the computation if you already reached the value, basically. But the thing that was trying to do was actually more simplistic. And let me show you. So in here, it was actually not doing that. So I know that if you want to get like the minimum value, so that it was just basically returning like what is actually the outcome. Under the assumption, so if you have a value, I'm just returning like the outcome of the game. So this function is just saying which should be like the outcome of the game depending on the strategies that I have at my disposal. So the value is just being returned is just the outcome, which is decided under the assumption that all the players are rational. And in here, where you have min or max, and then you have like GC in next move, is actually a bounded iteration. So you're iterating over all the possible moves, and across all the possible neighboring states, so from the given configuration towards all the possible moves that you could provide, I'm picking the minimum in one scenario. In the other scenario, I'm taking the maximum. So, and then, as a consequence, the action that I would prefer is the one associated to the score being the maximum. Then that is actually different. So then if I need to instruct then my agent what to do is I need to run my function recursively. Then that will also call as a consequence also the minimizing agent. But that you might see that as simulating the other opponent, like in my mental theater, so to speak, and also simulating my actions of my mental theater, and then picking the action that I might want to do under the assumption that the other agent is rational, and so it's trying to minimize their overall score. So that is actually the only thing, but that is actually the intuition. Then the other thing is that minimizing and maximizing will just return one value. So I'm not taking like a variable. So then if you want to implement, you need to take a variable, but that is very straightforward to have in this way. The actual implementation that you have in the code is more convoluted, but because we are trying to have this kind of runtime analysis. The other thing is that actually the other major difference is most of the time the decision trees or this kind of min-max trees are always set up, so they are always unraveled. In my implementation, I want to build those up dynamically depending on the score that is actually associated to the action, so that's why they're built up in that way. Otherwise, you would have been forced to create the tree in practice, so with all the possible configuration of the game. While the implementation that I already provide you only associate the action, whether increasing or decreasing the global value automatically. So you need just to change like the outcome for each action, and then the algorithm will automatically build up this increment within the implementation. And that is actually the bullet point 1 and 2 is actually the thing. So the underlying thing is actually one agent will try to maximize, the other one will try to minimize, and then I'm going to do the action leading to the minimization and the maximization. This is the only part which is implicit in the pseudocode. And so the problem is that if you're assuming that you have a branching factor of b, which I don't know if you're confident what that does mean. So branching factor is given one single setup, how many branches you're having from the parent node towards the child nodes. So that is actually a branching factor, which is b. And you have like a total depth of m, under the assumption that that is actually a maximum value. Then you know that in the worst case scenario, you need to visit an exponential number of states under the size of a branching. But still, so that is actually the time complexity to visit, but then this space for providing the solution is b times n, because it's just a square, as we were seeing before, with all the possible outcomes. Still, it might take some memory, but definitely takes a humongous amount of time to visit all. So that's why then we'd need to have another algorithm, which is called alpha-beta pruning. But before I progress with a reduction strategy, do you have any other questions related to min-max? Before I provide like the enhancement algorithm. Okay. So the idea is that I don't know how much you were coping with NP-complete problems, but whenever you have like an NP-complete problem, or you have still a problem which is massive to analyze, then the best thing that you can do is using like branch and bound techniques. You also have other approaches like greedy approaches, approximations, so on and so forth. But that one of the possible ways is to use branch and bound. And definitely, the degree of optimality will actually heavily depend on how you're setting up the tree, on how you're setting up the game, and anything of the sort. But still, in the best case scenario, so in the worst case scenario, you will not pruning nothing. So in the worst case scenario, you will fall down to the same scenario of min-max without alpha-beta pruning. In the best case scenario, then you will prove massively. And so you have like a reward. So, and in there, then you might assume how that works. And that works in this way. In this scenario, then you need to hit two variables called, namely, alpha and beta, or beta, depends on your understanding or pronunciation of Greek, ancient Greek, and the tradition coming from. Anyway, so, and they are respectively the minimum and the maximum bounds while visiting the tree. So, and initially, the maximum bound of alpha is actually minus infinity, because I want to maximize that. So any value which is greater than minus infinity will be better. So I want to get a bigger and bigger value. And similarly, the value for beta is initially plus infinity, because then I want to minimize that value with any other value, which is less than plus infinity. So how do you get that in C#? You might have like the greatest floating point or the greatest integer, and that is actually already provided in your programming language. And definitely then you want to remember, which is actually the best payoff that you met while visiting the tree. The rationale of the algorithm is the following. So if a maximum node picks a maximum value from any of the child, so J refers to the number of a child, just to contextualize the variables, then you know that all the other remaining childs proposing a value which is less than that one are going to be proved. And so that is actually when the mechanism will be triggered. Dually, if a min node picks a minimum value for the jth maximum child, all the remaining maximum children proposing a value which is going to be greater than that are going to be proved. Because that always works under the assumption of alternance. And then in here I have an example. But before I show you the example, I need to stop sharing. I have to show the entire screen. So one way to engage also with exam, so also the thing that I'm trying to do is to show you as much as possible topics also related to the exam. How do you exercise with min-max trees, alpha-beta pruning, because one of the exercises might be you have a tree and then you need to run an algorithm, either min-max or alpha-beta pruning on top of that. So that is actually more convoluted. Min-max alpha, beta, online. So you might want to use this kind of tool when you might add some, so, and then eventually you might add a value, and this algorithm will actually compute the solution for you. So if you are adding about, then I'm going to explain how the algorithm works, but I'm going to show you how you could automate the learning process by creating your own examples, basically. Then I'm going to show you, like, for example, just min-max. Then that is actually computing under the hood. Then the thing that you could do is see result, and then you would see what the min-max function was computing at each recursive call by providing the value in there. So just in here, as a useful example, why the minimizing agent was providing 2 in here, well, that is just because the min had to choose between 2 values, which were terminal between 2 and 50, and therefore it was deciding for 2. As a consequence of that is actually the choice. In this case, I have an unbalanced tree, so the other choice is just a non-terminal node, so it doesn't decide anything at all. And then the other possibilities are having a maximizing node on the top, and then the maximizing agent will still favor 2, because as you see, the agent is rational, so max will never pick -2, because that will come to the detriment of his strategy. So we'll try to pick also the best strategy for a minimizing agent. So albeit counterintuitive, still, if it would pick 2, it will disfavor him or her or it or them. And as a consequence, then it will just pick also the best strategy for a minimizing agent. So my suggestion would be, after you've seen this lecture, if you want to do a little of exercises extra, you might create your own tree and running the algorithm, especially with alpha-beta pruning, because that is actually the tricky part to understand how does that behave and how does the pruning happen. And that is actually one of the most tricky parts in the exam, really. So in here, the algorithm will start completely blank with just the minimizing node. Just out of simplicity, I already provided you the outcome, but I'm going to discuss with you together. So the minimizing agent will start having 8 or 6. So as customary, the minimizing agent at the very end will pick node 7. And that decision, having a 7, will be propagated on top. But you see, I also highlighted 3 in there for one specific reason. So I know that I'm visiting the minimizing tree, and then the value 3, I know that that will be picked by the minimizing agent. Then I know that the minimizing agent will have a value which is minimum, that is actually minimum, and that is going to be preferred, and the maximizing agent will never prefer the value being chosen by that minimizing agent. So as a consequence, I avoid visiting any further the value 9. So you'd see the order on which I'm providing the choices is also relevant, because if 9 and 3 were swapped, they could have not possibly pruned the tree. I could also prune the tree because the tree was adequately sorted in a way that the best choice was always the leftmost one, for example. So So that's why I could prune. Otherwise, I could not. As a consequence, then, I know that 7 is my final choice as a maximizing agent, then I'm propagating that on top. So you see, even in there, I'm pruning, but at the very end, not immediately. So, and then I need to go back, and then I have 7 will be the preferred one, but I have like 9 and 8, and then the minimizing agent will prefer 8. So I have like the maximum score of 8. Then I'm propagating that up. I know that the maximizing agent will provide a value which is always greater than my minimum value of choice, which is actually 7. So as a consequence, I will never favor 8, and therefore I will also discard visiting the other branch. And then I'm propagating 7 up. So in here, I'm just, out of simplicity, just using one variable, but the actual algorithm uses both variables. So that is just to get your hand around the algorithm, which is actually rational. You need to think about each time I'm swapping between alpha and betas. Then in there, I have the maximizing agent, but is that going to pick 7? I'm not sure. Then I need to visit the tree. Then always I will start with the minimizing agent having 1. And that is actually the final outcome, under the assumption that then I know, for example, that initially the only thing I know is actually the value 1. So why am I pruning that? I'm pruning that basically because I know that the maximizing agent will favor a value which at that stage is not necessarily 7. And in there, basically, the minimizing agent will pick 1, but I know that the maximizing agent will never try to get that value, so I'm basically pruning that up. And then I know in the next part that actually the minimizing agent will prefer 8/9, and so now the maximizing agent will prefer 8 out of 7, basically, and that choice is also propagated up. So even in there, I know that as a consequence, even the minimizing agent will prefer 8, but if I'm going back, then the minimizing agent will have a 9. Also, the maximizing agent then will potentially prefer a 9, and that will be never the best choice for the minimizing agent. So at that stage, I will definitely prune and avoid visiting also the rightmost branch, because I know that the maximizing agent will prefer that value of 9, which is also coming from the minimizing agent in this leftmost branch. And before I add probabilities to the equation, and then I will stop because we're running out of time, do you have questions on alpha beta pruning? Because basically the recursive function is basically the same with the addition of this alpha and beta values. Do you have questions related to how that algorithm works? So, yes.
So basically, as you go up the tree, you're pruning them based off the assumption that the agent's trying to predict what the other one wants.
Yes.
That you said, okay, that's the base of it. So if it's got high maxes down a tree, then even if the value is lower, the minimizing agent is going to prune that part of the tree.
Yes, because it's always working on the assumption that all the agents are rational. So I always know that I'm going to pick that decision. It's not because I'm going to prune that, then I'm going to change my strategy. Correct. So always the thing is the same. So the pruning is just how to reduce the search space, basically. I know that my algorithm will work in that way, so you do not need to think about like the agent doing that, but the machine mimicking the behavior of the agents. So I'm not even visiting this kind of assumption because I know that that will be never a final choice. From yes, where we left yesterday, do you have questions related to anything that was said yesterday or any day before that? So before I continue, by the way, this is just something that I already told you en passant, but really the thing that I wanted to show you is how you could then run the min-max algorithm using the code base that I was already providing you, and how that could be inserted like inside a main event loop inside your game. So inside the code base, you have like a realistic test class, and in there you have a use case example. So the thing that I would do now is give you an insight how that code works, and then you'll be free to adapt this setup to your game. So you have also a bunch of comments. They should help, but anyway, I'm providing you the rationale now. So if you go in there, then you see that this kind of AI is trying to provide all the assumptions for both the human player, and the non-player character. And in there, I have the player just providing two actions and an operation. For example, if I'm missing the hit or I'm not doing anything at all, and the non-player character just does a punch in here. So I'm trying to simulate a fighting game where you see in here, I'm not trying to orchestrate all the actions, how to reach the player. The actual turnout, the outcome that I'm interested is either I do something or I'm not doing something at all. And that is actually the only thing relevant for the progression of the game, nothing else. So that's why I'm not mimicking all the actions so to reach the player. That is actually uninteresting at all for building up the strategy. So then I'm creating a CGS, which is just the inference machine somehow. And then I'm creating like an initial tree-based game configuration. So the class is versatile, and in this scenario, this tree-based game configuration is just something specific to this scenario. But nothing prevents you from creating a new class. So you see here, I'm using that class within the min-max algorithm to say, this is actually the class that I'm using for representing my state, where strings are just the handler I could recognize actions, so to speak. And then I know that is actually my initial configuration of a game. And then inside this initial configuration, then I'm also providing, for example, which should be like the opponent life bar and the player life bar. And then, as I was mentioning to you before, just out of simplicity and in order to provide like a more effective computation, everything is normalized between 0 and 1. So one actually just says that they have the maximum health bar. So how do you cope with different health bars, which might be differently long and with differently amount of decrease depending on the power of the action? Then I'm just scaling up everything so to be within the interval between 0 and 1. And then in there, I'm assuming that I'm starting not with a player, but with a non-player character. So in this kind of turn-based machine, I'm saying that is the player turn equals false, and parent action being just an empty string is just saying when I'm starting the game, there was no prior action that I was performing. So the parent state refers to the parent action. So the action that that was done in order to reach this specific state. Then that is actually, then you have another part, which is just the definition of a lambda function, so to speak. And that is actually the main difference between using this code base and using a min-max trees as they are. Because usually, if you're using like a min-max algorithm, you need to hard code and implement all the nodes by yourself, by hand, and with a final state score. But that might be quite daunting, especially even if you have a very minimal game. So the thing that this is doing is simulating what is also happening in real scenarios when I'm using like real AI. I'm not creating the whole tree, I'm just providing the transition function from state to state. And so I know that if the player is doing, then I could perform some actions. Otherwise, if it is on the non-player character doing some actions, then I know what they might be about. So that's why you have everything defined through a transition function. And that is actually building up the health bar of opponent and computing the global total score. So in here, so this kind of condition that I have in here is just saying I might have like numerical errors when I'm trying to building up something. So if you do not know what numerical error are about, is because maybe you haven't done numerical representation within the machine module. But the idea is, whenever you're doing like floating point arithmetics or even doubles, then you are providing an approximation. The rationale is that any number which is not a power of 2, even a fractionary power, so 2 to a power of something, and the summation of these powers, then is always going to be like a periodic number. So even if you're trying to represent 0.1, it's going to be like 0.099999. So it's always an approximation. So you have like numerical errors that are going to build up. And in here, when I'm associating with the scores, the values that are 0, 1, 0, 5, and 0, 3, which are not powers of 2. Then you have also more sophisticated ways to detect whether the score is near to 0, but in here it's going to be more than enough that I'm picking the greatest value, which is less than the minimum value on which I'm decrementing. So I'm just picking 0.9. But usually in games also you're doing like the absolute number of that, if that is actually less than my epsilon number or anything of the like, but that is actually more coarse grained. So the thing that I'm detecting is if any one of the configuration is actually below the value, then I know that I stopped. So I create like a final state where the game finishes, and then I'm not doing anything at all. So that is actually what this line means. Otherwise, I know that I want to return, which is actually the current game state, so I'm returning this kind of result. And then I'm appending the action. So that is actually also different from the recursive function that you've seen yesterday. So by default, I'm not remembering which was the pathway leading to the given configuration, so I'm not remembering the chain of the actions, but I could always extend my tree, so in each state I remember the previous path that led to the current given configuration. So I might remember all the actions provided by the agents. So that's why you have this kind of append action to the game configuration. So I'm remembering that now the agent is going to perform an action now, and then I'm checking that, and I'm extending the current state with this action. And then I need to determine which is going to be the next move, and then I'm checking whether it is the player turn or the non-player character turn. So that's why I have this kind of if condition. Then, if I know that it's the player turn, and then I need to ensure that my transition function is correct. So that's why I have this kind of debug assert. Also, please double check that you don't have debug assert in C#, and that is actually so in Unity, because the library is quite different from standard C#. So you might be required to change, because debug in Unity is another kind of debug, which is not the default one. So you might be forced of changing some of the coding here. But anyway, then I'm checking whether the act is the turbo punch. Then I'm decreasing the opponent life bar of an adequate amount, which is in this scenario, I'm just decreasing the health bar by halving it. Otherwise, if it is just the mini punch, I'm decreasing that by 0.1. And then I'm creating a new configuration where the opponent has actually decreased amount. Otherwise, if it's the non-player character performing the action, then I need to update the player life bar, and then depending whether I'm doing a punch or I'm not doing anything at all, then I will have a different outcome. So I'm decreasing the score associated with a life bar. Then you have two ways to compute that. Either is using the min-max algorithm, but that might take a huge amount of time to converge and to compute the tree, especially if you have more than one action, especially if the amount that you're decreasing is very minor, and therefore it might take ages. So my heartfelt suggestion is to use the min-max, which will not compute all the tree, or not compute that entirely, and it will then, if you still need to navigate some part that were pruned initially, you will be able to rerun the game. So then the question that you might be asking is, how could I then use the min-max inside my Unity game? And that is actually the kind of question that I'm trying to answer now. So in here, I'm just creating like a truncated tree. So I'm using like the delta function, that was defined before to completely generate the tree while also doing the alpha beta pruning. So I'm also not generating the tree for the parts that are going to be pruned by the alpha beta pruning algorithm. And so the only thing that I have in there is actually truncated tree. Then if you want, in here I'm printing that to the terminal. Yet again, if you need to do that in Unity, then you need to disable the method because it's not using like the terminal printer, because actually you need to use the debug log or whatever kind of things that you have in there. Then in there is just showing you for the very beginning how could I determine the mechanic of a game. So under the assumption that the first player to run is going to be the non-player character, then it's going to determine which is the set of actions that are the best choice for both the maximizing and the minimizing agent, so both for the player and the non-player character, and is going to print that on the terminal. But still, that is not enough. That is just saying, okay, I want to do a battle, and then I want to get the outcome. That should be like the best scenario for both. But that is actually not really what happens, okay? So what it happens is that you have like a game running, and that is actually, so the thing on the top is going to be like in the exam, what is actually the best turnout, what is going to be the best decision. But it's going to be different applying that in practice in a realistic use case scenario, for which you might have different turns, which are written in there and constantly incremented. And then still at the previous step of the iterations, I'm creating the truncated tree. And then the top of the tree is actually determining what is going to be the action that the non-player character needs to do in order to win the game, in the best case, the best of the possible worlds. So then the non-player character only has two actions, the punch and no operation. So I'm only decreasing the score of the player, which could be like the health bar associated with the agent, only on that occasion. So if I'm doing the action, and in here I'm also decreasing the score of the player. I know that actually Unity one might be actually more complicated. You need to get like the game object, change directly the health bar, and that might be not triggered like in here, but might be triggered by an action that you're performing. So in here is just everything mashed up in one single line, but you might think that in that scenario I'm not decreasing the score, but I'm instructing the agent how to attack the player, for example, and to provide the punch and to do the punch. And then on the terminal, I'm saying, okay, this is actually the action that the non-player character has chosen. And then in here, I'm doing something that might appear weird, but it is not really. So I cannot navigate the tree potentially if the tree is pruned, because then I stopped expanding all the leaves, because I was running also the alpha beta pruning in order to determine the algorithm, so I was not expanding all the possible leaves. So some of the things are pruned. But it might happen that, for example, the player did a suboptimal choice, for which then I need to continue and expand the game. So that part was pruned, but not because my agent was wrong, but because the player was doing a suboptimal action. I was assuming that the player was always rational. It was not. Then I met like a pruning point, and then I need to continue expanding. And that is actually what I'm doing. So if that tree is pruned, after visiting the tree, then I need to refeed that again and to rerun the alpha beta pruning algorithm from that game configuration. Otherwise, I have like an action which is already navigating the tree. So at this stage, I am at, I am at the non-player character. So under that assumption, the non-player character is always doing the best action. That was the thing that I was doing on top. So in order to navigate the tree, I'm just navigating the tree and getting the next child having the best action. Even at this stage, after navigating the tree, I might have a tree which is pruned. Then I need to rerun the algorithm again, because it might be pruned due to the initial configuration that I have on top of me. And then I need to re-perform the action. So that is just braces and belts. And that is done cyclically, because that might happen at different sizes. Then otherwise that might be not pruned, and then I'm checking whether I reached a final state. So I have the children's size is equals to 0, So I know that the game actually stopped. No one could do anything at all. And then I'm checking whether I have a fatality. So I'm checking whether the score, either of the player or the non-player character, is less than the threshold. Whenever that happens, it means that they lost. And so I'm printing of a terminal fatality, then this player loses or the non-player character loses. And in this configuration, I remember the information from the state information, but you might have the same actual most updated information within your game engine. So that is just getting from the simulation. What the alpha-beta pruning algorithm is doing is mimicking the scenario, trying to be as realistic as possible, and trying to get the configuration. And by traversing the tree here, the thing that you're doing is getting the tree after the min-max tree is being computed, algorithm with alpha-beta pruning, and traversing the tree, following actually the actions that were done. So at this stage, then I'm detecting whether after performing the previous action someone has lost or won. Otherwise, I continue with my game, and then the thing that is performed in here is the part where I don't know, because actually I don't have like a player, a human player, using my keystrokes to do an action. So in here, the thing that it's doing is just getting the set of all the possible actions that the player might perform and getting a random action. So I cannot foretell. In here, I'm simulating a player doing something. The thing that I'm doing here is assuming that I could pick one of the three, turbo punch, mini punch, or no operation at all. So I'm taking element as the action that the player will do. And you see, even in there, then I'm having the turbo punch and the mini punch, and I'm decreasing the health bar. Even in this scenario, then you would have something different. You would have a player attacking the non-player character, and that detection might be triggered by like maybe a collision detection, from which you could establish how much you're decreasing, and that might be transferred into an action that is associated to a string, and then you know whether that is actually a turbo punch or a mini punch. And then by doing that, then the thing that you might want to do is to also continue navigating the tree, because okay, now this is actually the action that the player has chosen, and then eventually at this stage, when you have navigate tree with action, then you're going to traverse the tree that might be previously pruned, so you are still expanding under this assumption that that is pruned. Otherwise, if it is not pruned, then I continue to navigate, so I go to the next child state, and even in there I'm double checking. If it is not pruned, I continue to do that, and still I'm getting if I have a fatality and in either of the players. So that part of the code is actually the same. So if I reach the final state for which I do not have any kind of outgoing actions, then I need to determine the score and anything of the like. And then it has something very down below, which is the thing that we're going to see today. I was doing that only mainly because some of you were asking, okay, but can I use min-max or alpha-beta pruning for when I have more than two opponents? The answer is no, because it's going not to work properly. That was designed for 2 players, so that's why there is another algorithm which is max n, which we're going to see today, but we're not going to see the alpha-beta pruning variant because it becomes very obnoxious for me to explain and for you to understand, and it's not really worth it. So I'm just providing an example. So you could also use another algorithm that I'm also providing you if you have multiple players that are competing against each other, and so you have not necessarily cooperating, but you have like non-player characters being different. In here, just for the sake of the argument, I'm just providing everything as player and non-player character. I'm not providing the thing with 2 or more players, but actually the configuration is more or less the same. I'm providing like transition functions, a lambda function, which is then used to fit the tree. And for this, I'm not providing like the main event loop, but the idea is actually the same. At the end of the fitting, you're just generating the tree of all the possible outcomes, and then that tree might be used inside the game. So the thing that I was missing to tell you about is that everything in there is actually within a while true loop. which is this one. So I'm continuing to run the game. Similarly, as in Unity, where you have like the built updates, where you're going to run the update method. And so you might see like this part being inside an update method, so which is actually determining what to do. So that is actually one suggested way. I'm providing an example. I'm not doing that in Unity because that should be your exercise on how to inject that code, but that is actually the rationale of what the behavior of the code should do if you want to use that to instruct a non-player character how to choose among the actions. So I know that that might be trivial because you don't have like a complete strategy, and in here you just have like one action, turbo punch, mini punch, or one punch, which is actually not a great deal, but still you'll be aware how to showcase the usage of AI. So we're not interested in doing something great, but just that you understood how the technique worked and you were able to apply it to the coursework. That is actually all we were looking for. We're not looking for A-triple games. Then whenever you're going to the industry, eventually you will be working on A-triple games, but you cannot achieve an A-triple game in a very few months. So we are just expecting from you to understand how to use the technique, not to do something extraordinary. So also applying that for solving a very simplistic problem, that could also do. So that is actually an intuition how I'm bridging the gap between the theoretical part explained yesterday and actually the code. So my suggestion will be for you to engage with this code base if you have problem understanding the slides and double check how that code works. So I provided as much as possible comments to explain how that works, but it might be somehow complicated. So that's why this is actually provided as a library. And I will just restate myself, but that is also fine. You are not forced to re-implement all this kind of stuff in your coursework. So you might exploit that kind of library as it is. So that's why even in the code base, you have min-max library and min-max projects. So the library is by itself just the classes, so to make the algorithm works, and then you have the projects which are just an instantiation of the library usage. So you might also compile the DLL from the top and include that in Unity, or include all the scripts from the thing on the top, but still the major dependencies are the things on the top. Any question regarding this code base, on how that works and how that might work in your coursework? So briefly, as just as a summary, the idea is the alpha-beta pruning or min-max algorithm will just return a tree eventually, which is the full combination. And if you have alpha-beta pruning, that tree might be also pruned eventually. The idea is, how does a non-player character exploit the tree? Is just navigating the tree after being pruned. So with a difference that for which, so in as much as the NPC is concerned, it's going to follow the best action. So is exploiting the tree to get, okay, I know that now the best action for me is this one, therefore I'm navigating the tree, following the best child. For the player, I don't have control, because I cannot assume necessarily that they're going to provide the best action. So I need to receive the action, and after receiving the action, then I know that the player is performing this, and this information will be the one that I'm going to use to navigate the tree. And then after doing that, I'm doing that in a loop. So I'm determining whether the game needs to continue because I haven't determined yet which is going to be the winner, or if I need to stop. So that is actually just, in summary, the rationale of this code. Then let's see. That is just, I will just briefly mention this, which is actually the thing that I was saying yesterday. So before this kind of hype on neural networks and the like, the majority of artificial intelligence started with logic. So you have also horn clauses, like you had like datalog. So you had all the techniques were logic-based. Then they were not able to optimize that in a good way, so they restrained to using neural networks, but at the very beginning, they were not necessarily using the other technique. just to say that for some problems you could still use non-neural network techniques. So in fact, how does Deep Blue work in order to beat Kasparov at playing chess? They were actually using the min-max algorithm, using alpha-beta pruning. So this information is actually available online if you're just looking at YouTube videos, people explaining how the challenge worked. They're actually explaining the same stuff. There are also people at MIT or Carnegie Mellon that are explaining that. So if you're checking their lectures online, that is actually where I got the sources of, not industrial secret. And then they had even more pruning strategies. Alpha-beta pruning is just one way. But if I'm assuming that the gamer is actually a professional, then I could avoid exploring some states even from the very beginning, even without the alpha-beta pruning, just providing assumptions. And even in there, that might be the problem, as we were seeing before, that it's really dependent, the power of pruning, on the way I'm ordering the leaves. And definitely there might be a problem if those are not sorted properly. So they are ensuring that the leaves are sorted properly so to achieve pruning, and they were trying to cope with a tree which is not very well balanced, so to run the algorithm. And definitely, even though you are considering a depth of 7 moves, still the game of chess could go on indefinitely. And so you have a massive amount of possible outcomes that you need to consider. So they were using massively parallel computing. So they were partitioning the problem so to solve sub-problems and then recollecting the answer and getting the best answer out of each sub-problem itself. And as I was saying yesterday, you know that the player is going to use opening moves, or you know which the final moves are in the game. So you could prune massively by knowing what other player know. And that is actually how they were using a non-training based AI to win still never get less of the game, but just knowing which are the rules of the game. And definitely also the board configuration is going to be massive. So you cannot do like in tic-tac-toe and provide all the possible configurations. So there were also techniques to summarize the board and know if some two strategies were equivalent, despite the board being configured differently, and then merging the states. So you could do that. It's just a great amount of work. While if you're using neural networks, you have Harry Potter magic coming out of it, but then you don't know why it is computing something like that, whether the outcome is detecting something right for the right motivation. And here, everything is provable, what you are doing. And so, the other thing that I wanted to show is why also probability might be injected in this kind of games. Because right now, we just assume in games like chess, where actually you have no rolling of a die. But you have other games like backgammon, where you have also other moves that are forced somehow. So I have the free will, for example, as a player, to move my checkers around the table, but I cannot predetermine how many steps I could do or how many checks in the table I could move. And everything is actually forced by the rolling of the dices. So the player rolls 2 dices in this result, and the resulting value will tell how many move along the checkers along the triangles. So I have a strategy. I could also decide where to move, how many checkers to pile up, but still is limited by the turnout of the dices. And so you have some rules in this game, but we're not going to dwell into much details. So then a checker cannot move to a point containing at least one opponent's checker, and single checkers might be pushed by the opponent towards the beginning of the game. So that is actually a refinement of the game of R. So you have also 2 games. One is actually called, because actually Parkis, on which you could also defeat the other opponent, and then you have also the game of R, when you could also kick the other player, and that should restart from the very beginning. So then this kind of game was actually refined through the centuries. So then you have a strategy. So the strategy is actually you're starting from your house, and then you need to complete the cycle and go back. So go back to home, basically. And you need to complete your turn, similarly to the game of R. Well, and then you could also build up a strategy so to make all the checkers in the board to be pushed for your opponent as much as possible, so it might delay its arrival to the home, because actually the target of the game is make all your pieces go back to home. So you want to delay that as much as possible. So that's why, given that you have also probability, then you have something which is actually unpredictable, not even because you want, so that is actually also the difference. Until now, we were mentioning that in order to achieve unpredictability, you might use a random number generator, so to change the action of your non-player character. In here, the random number generator is also something external between the two. Both the player and the non-player character is actually an external force, which is forcing a given direction of the game. So it's the force majeure that I was telling here above. So the dice roll restrain the set of the possible moves that the player can perform, but because actually I could only do a specific kind of move, and I cannot move my pieces freely. But the free will is still on the kind of pieces that I could move across the board, because I might have different pieces and I could decide to move this piece by a given amount. And still my free will is, if I'm moving this check, then I could also end up in a given position and push away the other checker of my opponent, so he's forced to restart. So that is actually the main motivation of having this kind of game with probability. And so then that also requires you to extend the transition function to also encompass probabilities. So you see, probability is also something that you're adding afterwards, not something that you're given for granted from the very beginning. So then you have expected min-max, on which, if you have like a roll of a die determining the outcome of the game, then the only thing that you could do is to average out the possible outcomes. You cannot decide, okay, my best outcome will be when the die will have this value configuration, so somehow I'm assuming that the die its outcome will be like that, and therefore I'm forcing that in the game. It's not going to work. So that's why I'm averaging out all the possible outcomes, for example, given the probability of each outcome. So that is actually the line here in orange of whichever color you're perceiving. So you have GC that at this stage will be your random number generator. And then you have like a probability for transitioning from a state GC towards a next state that GC is going to entail. And the probability of transitioning towards this state will give you the value to do the weighting on the expected value. And that is actually also good, because if that value is going to maximize my score, but the probability of achieving that configuration is very low, then I'm not considering this strategy at all as the best strategy. I'm considering then a strategy which will be more likely, and the likelihood will weight actually how much I need to trust this operation. So the outcome of this algorithm is that then each player will decide to move to the next state dependently on the turnout of the rolling of a die. So the rolling of a die is going to just to choose which is going to be the next configuration. So the next configuration, depending on that game, is all the moves should be of this kind of amount. And then the next state will be actually dependent on the strategy that I'm applying under that configuration. So the non-player character or the player should take the state associated to the best outcome given the average. And that averaging out that value will provide like the average value that the player is receiving from that potential configuration. So, and even in there you have a code, you don't even have the code base in here. And you also have pruning strategies for this algorithm, but those are starting to become more complicated, because then you need also to know what is actually a Monte Carlo sampling algorithm, but you didn't do like a probability module, so it's going to be like obnoxious for no reason at all to explain. Also what is Monte Carlo sampling, how that is applied to that. So all you need to know is that you also have pruning strategies for these scenarios, but actually everything boils down to a roulette game. Just spinning out and just sampling, random sampling, and then getting out values out of that. So that is the best thing I could do. And that is actually what Monte Carlo sampling is about. Running a roulette, getting the outcome, and getting between the data space that I'm sampling, which is the best possible turnout. And that's pretty much it. And then the other thing that, as I was mentioning previously, you could also have another configuration across multiple players, as I was mentioning. But if I want to apply my min-max algorithm to multiple players, then I need to assume something different. So it doesn't work that you have one single score. And in here, the thing that it works is that you have like a single score, similarly to the health bar, associated to each of the players. So that is actually going to be simpler to understand for you, given your mindset, and still different from the previous one. So then the change of the algorithm respective to the previous one is just that you're not updating a global score, rather than updating a value, a specific value within the vector, and each player is actually going to be associated to each specific position within the vector. So you might freely assume that each position will be reflecting the value of the health bar associated with the player. And so each leaf will contain just the health bar configuration across all the players at the end of the game. And each non-terminal leaf will contain just the parent strategy, and will run the algorithm similarly, and will choose actually the action maximizing its own component. So I cannot care less about the values of the other opponents. I'm just focusing on the maximization of my single value. So, and that is actually similar to a greedy approach and more in line of what you might be thinking about, even from the very beginning. You see, this kind of mindset, which is nearer to what you're expecting, is actually coming in a more complicated setup, which is counterintuitive. And that is actually what you're doing. And so the first line of the pseudocode is actually providing the vector and the score configuration for each of the players. So if you reach a final state where the game ends. Otherwise, and that is actually the last line is actually reflecting what I was saying, within the vector, and that is actually this part in here, max n GC on the slide, I. That is saying I'm only considering the ith component of my vector. And still, I'm getting the recursive call, so I'm getting what is the configuration associated to this state. But then I want to maximize the value only related to this specific setup. And then the rest is the same. So I'm preferring to transit towards the state, maximizing my own value. So I'm not maximizing a global value, 0, 1, minus 1, but just the value that is maximizing my own turnout. And so you might have something similar to this. So similarly, all the examples that you have written in there, so that's including also the min-max alpha beta pruning that you see in the previous slides, and also this example are all provided in the code base, and they are coded from scratch. So you could also double check the running of this algorithm and the previous ones by looking at the slides and running the code that I was discussing today. So you have that really in yes, so you have another class which is max n test. We're actually having this kind of final configuration. So I'm setting up all the actions which are just moving left or moving right. So you have 0, 1, 0, 1. And then at the end, I'm having actually the final state with the values associated to that. and then I'm running the algorithm. So that is actually what I'm mentioning. So you have not only the code base, but you also have the slides, and you have opportunity of running the code using like Visual Studio and using C# and running the code. And that will actually show you this kind of tree being printing out. And that will actually say what is going to be the preferred action to be performed. In this scenario, it will be what? And in this scenario, 1, 2, 3 is merely reflecting the agents playing. So in here, you don't have min, max. You have 3 agents because you also have a vector of 3. So each number inside the squares is reflecting the player ID. So it's different from the previous tree where the node contained the value that you were computing, the global value. In here, squares just provides the player ID. So then 1 is actually peaking one state, then 2 is peaking across the other states, and so on and so forth. So, and even in this scenario, you have also optimization. So, similarly to the sampling approach when you have probability, even this comes with an optimization, but we're not to discuss that. So that's why I'm saying keep it simple and keep it short. There is also the possibility of optimizing this algorithm, but you need to constrain your problem. So you need to ensure that whenever you're setting up a tree, then the value is actually always a constant value. So what does that entail? In practice, you could optimize if you're freely assuming that all the life is lost is actually accumulated somewhere else. Like, for example, in the world, which is keeping count of how many lives or how many pieces of a health bar were lost. And everything that was lost is going to be shifted into a non-existent layer, thus ensuring that all the life, the sum of all the health bars, always add up to the same value. But that is quite counterintuitive, but that is actually something that you could do. And then on top of that, if you're assuming that, then you could also optimize the algorithm and doing something similar to alpha beta approach. So the only message that I wanted to provide in here is that you could always optimize each approach, and then depending on the complexity, either I need to do random sampling or I need to drastically change the algorithm. But it should be always good to optimize. So why I was introducing probability now? Because then I will introduce the usage of probability in state machines next. So I will just do it like a brief introduction, and then we're going to recap next week for sure, because I only have 10 minutes. So before I start and continue, do you have questions related to the code base, related to this thing, or anything else that you wanted to ask before I continue? Yes.
So for this, like code and algorithm here, like it says like you're not going to like go into like detail about this. So I'm guessing we won't be asked about it in the exam.
Correct. Correct. So you might be asked about alpha beta pruning. You might be asked about min-max. You might be asked about what is expected outcome. You might be asked about max n, but whatever I'm not providing details, you're not going to be asked. Thanks for asking. So that's why I'm providing, is more for you really to provide, okay, so it's just to say, it's not because I'm not talking about this that does not exist. That is actually the only point that I wanted to make. But, so if you had more time and you had more experience, then I could also teach you how to optimize max n, how to optimize and branch out the expected min max, but that is not required. For you, the only thing is you are aware that they exist, but you're not going to be asked those of exam. It doesn't make any sense to ask you something that I was not teaching you. Any other question? So my suggestion would be also depends really much on the mindset either engage with the slides or engage with the code. Every example that you're going to see, you have examples in the slides and in the code.